Greetings everyone, my name is Bernardo Pereira. I'm a PhD student at the Universidade Federal de Minas Gerais in Brazil, and today I'll be talking to you a little bit about the use of solar-like oscillations in the characterization of red giants. So solar-like oscillations are produced by the turbulent motion in the convective envelope of stars, and they can be observed as brightness or radial velocity variations. The pressure modes are characterized by having specific frequencies with a semi-constant spacing proportional to the large frequency separation, and by having amplitudes modulated by a Gaussian envelope centered in the frequency of maximum power. They are usually observed in stars with masses between 1 and 3 solar masses and radii between 1 and 15 solar radii. Therefore, they can be observed not only in the main sequence, but in the subgiant branch, the red giant branch, and the horizontal branch. The global properties of the oscillations, that is, the large frequency separation and the frequency of maximum power, are related to some elements of the stellar structure, as shown here on those relations, where we can see that the large separation is related to the mean stellar density, and the frequency of maximum power is related to the surface gravity and the effective temperature. Therefore, those quantities can be used for characterizing stars. In my work, we use the Basti grid and the Yale-Birmingham method to determine the masses, radii, and ages of 12 red giants with solar-like oscillations. Those parameters were important for those stars because they are also exoplanet hosts. The methodology goes as follows. We first take the observational parameters of the stars, and this includes not only the seismic properties, but also other observational parameters. We compare those parameters with the models from the grid using the likelihood function, and then we determine the masses, ages, and radii by averaging the models with the highest values of the likelihood. The process is then repeated several times by adding noise to the observational parameters so we can have a more robust determination. I'll show you the results on this figure right here, and we will compare them with some previous determinations from non-seismic works done for these stars. For the radius, we can see that our results are pretty consistent, but we have a great improvement in the uncertainties. For the masses, there was also an improvement in the uncertainties, but the most striking feature is the fact that the masses from the seismic analysis are smaller than the ones found in non-seismic analysis. Finally, for the ages, we see the opposite behavior, with the values from the seismic analysis being larger than the ones found in the non-seismic ones. Those differences for the masses and ages have been observed in other seismic works. And they are usually attributed to the fact that when you introduce the seismic parameters in your analysis, the differentiation of models of the grid is done in a more efficient way, and this leads to new determinations for those parameters. We'll see a practical example for the star of number 6 right here. I started by doing the characterization of this star without including the oscillation parameters. And you can see the results right here. For the radius of the star, we have a single determination. But for the masses and ages, we see an ambiguity with two possible values for those quantities. And to understand why this behavior happens, we need to look to the models that contribute to the solutions. This is shown right here on this HR diagram. We see two stellar tracks that represent those two solutions right here. And we see those black points right here that symbolize the values for the observational parameters for the star plus the noise that we added. And we see that on this region, the red giant branch of the blue track intercepts the horizontal branch of the red track. And this leads to those two different solutions because with only using magnitudes, effective temperatures, and metallicities, there's virtually no way of differentiating those two tracks right here at this region. When we add the seismic parameters, however, because they are related to the stellar density and the surface gravity, they should be able to differentiate those two tracks and show which one actually represents the star. And this is what actually happens when we include the oscillation parameters in the analysis. We see here that our results converge to the solution that has the smaller mass and the highest age. I'll wrap this up by showing you the references used in this presentation and by thanking you very much for your attention.